Hello and welcome to yet another video of Cornerstones of Math. This video will be released at 12:30 on Christmas Day Korean time, which is quite close to this special time that occurs during this Christmas. In this year of 2025, it is possible to have the time, the year 2025, December 25th, 25 minutes and 25 seconds past 12 o'clock, where the number 25 is repeated 4 times. And there's also number 12 repeated twice, but that's pretty boring compared to the case of 25. To commemorate this special time, let us try to find the prime factorization of the 8-digit number 25252525, that is 25 repeated 4 times, which can be also read 25,252,525. Obviously, one method that works is dividing by every prime number, but since that is boring, let us not rely on that tedious method. Or at least, let us try to use that method as little as possible. We will still use this list of prime numbers, because not many of you might have memorized these many prime numbers. The first thing we can do is to apply some familiar divisibility rules. Notice that this number ends with 25. This means this number is divisible by 25, which is 5 squared. And you can actually do this division in your head. It gives 25 times 1010101, hence 5 squared times 1010101. Now let us take a closer look at this number. From the list of prime numbers, you can see that 101 is a prime number. Some of you might already know this. And we have 101 here and 101 here. This means that 1010101 can be written as 101 0000 plus 101, hence 101 times 10000, hence 10,000, plus 1, hence 101 times 10,001. Therefore, we have 5 squared times 101 times 10,001. As for 10,001, which is 10 to the power of 4 plus 1, things get a bit complicated unfortunately, and I will use modular arithmetic in the explanation. In a nutshell, we want to find some prime number p such that 10 to the 4th power plus 1 is congruent to 0 modulo p. In other words, 10 to the power of 4 plus 1 is divisible by prime number p. This can be written as 10 to the 4th power is congruent to negative 1 mod p. We can square both sides, which is one of the most basic properties of modular arithmetic. This gives 10 to the 8th power is congruent to 1 modulo p. So we obtain the equivalent task, which is finding the prime number p such that if we divide 10 to the power of 8 by p, we obtain the remainder 1. And this is where we need another theorem, which is the famous Fermat's little theorem. This means that by integer a and a prime number p, a to the power of p is congruent to a modulo p. Or equivalently, if a and p are co-prime, then a to the power of p minus 1 is congruent to 1 modulo p. And we are going to use this second version of the theorem. Let's go back to this part. 10 to the power of 8 is congruent to 1 modulo p. By the exponentiation property of modular arithmetic, we know that 10 to the power of 8k, where k is a positive integer, is congruent to 1 modulo p. Let's compare this with this statement of Fermat's little theorem. By comparison, we can gain following intuition. Maybe there is a possible case when p minus 1 is equal to 8k, the multiple of 8. That is, p is equal to 8k plus 1. So our task is now limited to finding a prime factor of the form 8k plus 1. The prime numbers of the form 8k plus 1 are 17, 41, 73, 89, and so on. Unfortunately, there's no way around the brute force here, so we have to do a bit of brute force of dividing by these prime numbers. Still, you will quickly find out that 10,001 is divisible by 73 to give 10,001 equals 73 times 137. And both 73 and 137 are prime numbers. Therefore, the prime factorization process is finished, and we obtain the final expression 25 repeated 4 times is equal to 5 squared times 73 times 101 times 137. And that's all for today's video. Please don't forget to hit that like and subscribe buttons if you enjoyed this video. And even though this is not my last video of this year, I wish all of you to have happy holidays and happy new year.